Well, welcome, ladies and gentlemen. You don't always have an introduction to meetings, at least certainly we at the British Academy don't always as beautiful as the one you've just heard, but sadly brief. My remarks will be equally as brief. As President of the British Academy, my name's Adam Roberts. I simply want to give you a very warm welcome in the name of our Academy, which is the National Academy for the Humanities and Social Sciences. And I can't resist making one personal observation at this event where we are commemorating, celebrating the Gifford Lectures. And that is, I note the Gifford Lectures have been going on for 125 years, and that there is a strong Scottish connection. And I have to say that my grandfather was a Scottish theologian who worked at the universities of Glasgow and Aberdeen, where he was the principal for many years, and it is inevitable that he will have attended, possibly even given, a series of Gifford Lectures. So although I can't claim a personal, direct connection with the Gifford Lectures, I feel that there may be one in my DNA. Like all of you, I'm looking forward hugely to what the panel has to tell us about the reflections on these lectures. And now I hand over immediately to Jack Templeton to introduce the meeting. Thank you.
Well, good afternoon, everyone. Many thanks to Professor Adam Roberts. Thank you for hosting us here. This is a great treasure for all of us. It's also a privilege to be gathering once again in these gracious surroundings in the beautifully renovated home of the venerable and distinguished British Academy. I particularly recall a visit here 5 years ago. It was May 2007 when Charles Taylor gave his Templeton Prize lecture in this very auditorium. This year, 2012, is the 40th anniversary of what my father established that is now known as the Templeton Prize. But even more remarkably, it is the 125th anniversary of Lord Adam Gifford's establishment of the Gifford Lectures. He did this through his generous bequest to 4 ancient Scottish universities, Aberdeen, Edinburgh, Glasgow, and St. Andrews. In one sense, when he did this, each of these universities could be called ancient. But I think, and I think my father felt, that he saw each of these Scottish universities at the cutting edge of scholarly inquiry. Lastly, if I may humbly do so, this year, 2012, is the 25th year of the launch of the John Templeton Foundation, but not in a small part, I think inspired in Sir John's mind by the 100th anniversary that year of the Gifford Lectures. Last month I was in London for the awarding of the 2012 Templeton Prize to the Dalai Lama at St. Paul's Cathedral. It was an honor to meet him, but it is no less of an honor than to have with us here today 8 past Templeton Prize laureates, especially from the last 15 years or so. 7 of them, Ian Barber, John Barrow, Freeman Dyson, John Polkinghorne, Holmes Ralston, Martin Rees, and as I just mentioned, Professor Taylor, have all been Gifford lecturers. In almost all the cases, as I recall the nominators for each of those laureates, they almost always drew very heavily on these laureates or presumed nominators as laureates from their various Gifford lectures. We are also privileged to have today as the moderator of our first panel, George Ellis, who himself received the Templeton Prize in 2004. I'm absolutely delighted as well that we have Keith Ward, a fellow of the British Academy and a former member of the Board of Advisors of the John Templeton Foundation, who will serve as moderator of the second panel this afternoon. My father, Sir John Templeton, was born 100 years ago this year. He lived through amazing experiences, often as a witness, often as a studier, of things happening and changing in business and finance, in the earth-shaking turbulence of the 20th century, but most especially in the dynamism of science. And of course, during his 95 long years of life, he became aware of new philosophical and theological ways of understanding or interpreting reality. He always believed that wisdom involved a genuine openness to new ideas, and also to be confident enough to prompt new ideas from so many innovators, not the least from so many of you who are with us today, by just simply suggesting or raising what might be called multidimensional or multidisciplinary type of questions. So I know that we're all looking forward to hearing from our distinguished panelists how the ideas that they put forth in their earlier Gifford lectures may or may not have changed over time, but most particularly, why. So on behalf of Sir John Templeton, again, welcome and thank you very much for being with us today. Sir.
Well, I'm George Ellis. It's a great privilege to be here to act as chairman for this session. You have in your little books detailed biographies of each of our speakers. They're extremely distinguished. They are all fellows of the Royal Society of London. They are all successful popularizers of science. But really importantly, they are all broad-minded in their philosophical views. They are not part of the current wave of reductionist science that we've had quite a lot of publicity about in recent times. They are all Gifford lecturers and they're all Templeton Prize winners, so it's a very distinguished panel. I just have one comment that I'm really, really sad that in the list of Templeton Prize winners, the person who was a Gifford lecturer who's not there was Arthur Eddington. Now, Arthur Eddington was one of my heroes, one of the great Gifford lecturers, and of course he died before the Templeton Prizes began, and I'm really sorry about that. So without further ado, I'm going to take them in inverse order. So Martin Rees, the past president of the Royal Society and very distinguished astronomer, astrophysicist, will be the first speaker. You have 20 minutes.
Right. Thank you, George. Can I start by echoing what you say about Arthur Eddington? I was fortunate to hold the chair that he previously held, and he is someone who inspired us by his research and his eloquence. Well, it's not surprising that cosmology and astronomy figure quite significantly among the Gifford lectures over the last decades, because cosmology is a fundamental science, and also astronomy is one of the grandest environmental sciences. Indeed, it's perhaps something we share in common, because the night sky is the one part of the human environment that's been shared by all human beings throughout human history. They've stared up at the vault of heaven, interpreted it in their own way. And that's why it's also among the big questions which the Templeton Foundation is keen to foster. Well, this is a subject where things change fast, and a lot has changed since I gave my Gifford lectures. There's been a real crescendo of discovery, and the discovery is owed largely to better technology. Armchair theorists deserve little credit. And in particular, we've learned in the last few years something that makes the night sky far more interesting to us than it was to our forebears. We've learned that most stars are orbited by retinues of planets, just like the Sun is. These planets are detected indirectly by two methods. The first method is to detect the motion of a star induced by an orbiting planet, precise Doppler measurements. This can detect big planets, rather like Jupiter and Saturn, the giants of our solar system. And several hundred stars have been found to have big planets orbiting them by this technique. One has as many as 7. Another more recent technique is being used by the NASA Kepler spacecraft, which is looking for transits when a planet moves across in front of a star, as indeed Venus will move across the face of the Sun next week. What happens then is that the star gets marginally fainter because the planet blocks out a bit of its light. And if, for instance, the Earth moved across the face of the Sun, and you looked at it from a long way away, the Sun would get fainter by 1 part in 10,000. And the Kepler spacecraft is looking at a part of the sky and measuring the brightness of over 100,000 stars to a precision of 1 part in 100,000, and doing this over and over again, several times per hour for each star, looking for regular dips caused by orbiting planets. And it's already found evidence for a number of planets no larger than the Earth. But what we have to wait 10 or 20 years for is a real image of an Earth-like planet, rather than just detecting its shadow. And to illustrate what's involved there, let's imagine you were an alien astronomer with a big telescope looking at the solar system from 50 light years away. The sun would then look like an ordinary star, and the Earth would look, in Carl Sagan's nice phrase, like a pale blue dot, very close in the sky to its star, our sun, and much, much, much fainter. So you're looking for a firefly next to a searchlight, as it were. But if the aliens had a big telescope and they could look at the pale blue dot, they could learn quite a bit about it, because the shade of blue would be slightly different depending on whether the Pacific Ocean or the landmass of Asia was facing them, and they could infer, therefore, that there were continents and oceans, the length of the day and the seasons, maybe something about the atmosphere. Now, in 20 years, we have telescopes that can do that for Earth-like planets around other stars. That will indeed be exciting. Then, of course, the question is, will there be life on any of these planets? Here, I think we just don't know, because we know too little to say whether life is likely or unlikely, because we don't know how life began here on Earth. Was it a rare fluke, or is it something that would happen in the environment? And although it makes sense to look first for life on Earth-like planets, we shouldn't look just there. I think Freeman Dyson is going to talk about this topic, but I think science fiction writers have lots of ideas about how life might exist in other very different kinds of environments, and I think indeed it's better to read first-rate science fiction than second-rate science. It's more interesting and no more likely to be wrong. Well, even if simple life is common, it's a separate question whether it's likely to evolve elsewhere into anything that we might recognize as intelligent or complex. And as you know, there are some searches being done for this sort of thing. And, of course, now we are pessimistic, but it's interesting to realize that in earlier generations, the idea of a multiplicity of inhabited worlds was quite common. I mean, Giordano Bruno famously, and Thomas Wright of Durham was an early believer in the plurality of worlds. And let me give a quote from Thomas Wright, who imagines the universe teeming with life. He says, "In the great celestial creation, catastrophe of a world such as ours may be no more to the great author of nature than the most common accident of life with us. In all probability, such final and general doomsdays may be as frequent there as even birthdays with us upon the earth." So the idea of many, many systems with intelligent life was widespread, and it may still be correct, we've no idea. On the other hand, maybe ET doesn't exist. Earth's biosphere may be unique. And that would be disappointing for the searchers, but it would have its upside, because it would entitle us to be less cosmically modest, because our tiny planet could then be the most important place in the galaxy, perhaps even a seed from which life could spread through the galaxy in the far future. Wittgenstein famously said, "If a lion could speak, we couldn't understand him." So, if we found aliens, would the culture gap be unbridgeable? I think not necessarily, because they may be on planet Zog with 7 tentacles, but science would be a common cosmic culture. They'd be made of the same kind of atoms as us. They'd gaze out, if they had eyes, at the same cosmos. They'd trace their origins back to the same Big Bang. This leads to my second topic, the cosmos on the grandest scale. Here there's been rapid progress. Powerful telescopes can image newly formed galaxies whose light set out when the universe was less than 10% of its present age. And high-precision measurements of the afterglow of creation, the weak microwaves that pervaded galactic space, allow us to trace cosmic history back to an era when every particle carried as much energy as the LHC in Geneva can produce. That's when the universe had been expanding for a nanosecond, and when everything we can now see with our telescopes would squeeze down to the dimensions of our solar system. But as always in science, each advance brings into focus some new questions that couldn't previously have even been posed. For instance, why is the universe expanding the way it is? How did it get its observed mix of particles and radiation? And the answer to these, we suspect, lie in the brief instance when our universe was far less than a nanosecond old, and everything in it was far hotter and denser still. But there we lose any firm foothold in experiments and enter more speculative realms. There was a nice magazine cover I saw which showed a little red disk, and the caption was, "The universe, when it was a trillionth of a trillionth of a trillionth of a second old, actual size." And indeed, according to the most popular theories, many of the key features of our universe were imprinted when everything that we can now see with our telescopes was squeezed down to the size of a tennis ball and inflated from that. How can we firm up such an idea? The twin pillars of 20th century science are, of course, Einstein's theory of gravity and the quantum principle. But these haven't yet been meshed together. For most of science, this doesn't matter, because in a molecule, the gravitational forces are weaker by 40 powers of 10 than the electrical forces. They can be ignored. Conversely, an astronomer thinking about the orbits of planets and stars doesn't need to worry about the quantum fuzziness of those orbits. So we've got on fine without having this unified theory. But if we want to ask seriously what happened when the entire universe was squeezed that big, then we have to contemplate that quantum fluctuations could, as it were, shake the entire universe. And there are reasons to suspect that the fluctuations that eventually gave rise to galaxies were imprinted at that time by quantum fluctuations. So that is a challenge for the future. Another related question to the beginning is the question, how big is our universe? And this is not a trivial question. The region we can observe with our telescopes is 10 or 15 billion light years across. There's a sort of horizon which is delineated by the shell such that the light can just get to us along curved space since the Big Bang. But there's nothing magic about that horizon any more than there's anything magic about the horizon if you're on a ship in the middle of the ocean. And if you're in the middle of an ocean, you don't think that the ocean necessarily ends just beyond what you can see. You suspect it goes on a long way. And ditto in the case of our universe. There is very strong reasons for suspecting that there are many, many galaxies beyond the reach of our telescopes, and that the universe goes on at least 1,000 times further than we can see. And many people suspect it goes on much, much further even than that. And moreover, if you're worried about unobservable entities, the fact that the universe is believed to be accelerating means that many galaxies that we now observe will eventually disappear over the horizon, and the future of even present-day galaxies will be in principle unobservable. But there are many galaxies that we will never observe even at all. And the universe could extend even more than 1,000 times further, hugely further, maybe so far that all combinatorial options are fulfilled. You all know the story about the monkeys on a typewriter, given enough time doing the works of Shakespeare. Well, if all the planets in the observable universe were crawling with monkeys who've been typing for 1 billion years, they'd have got one sonnet, that's all. So you need a much, much bigger universe to have all the combinatorial options to write everything, and of course to have duplicates of ourselves. But if the universe is big enough, then all combinations are fulfilled, and there would be somewhere out there a duplicate of this lecture room. And indeed, I'm not sure if it's any comfort, but we will have an avatar out there, and if we make the wrong choice, we can be confident that out there our avatar may have made the right choice. Well, the universe beyond our horizon may be huge, but that's not all, because this is just the aftermath of our Big Bang. And the other recent development is that there are some theories which suggest that our Big Bang may not be the only one. There are many variants of this multiverse scenario, but they're still speculative because they depend on specific details of the still unknown physics at 1016 GeV when the universe was that size. But you can say what the specific requirements are on that physics for particular things to happen. And the Russian cosmologist Andrei Linde in particular has shown that for particular assumptions, which are indeed thought quite plausible, then there would naturally be, as it were, a grand version of the old steady-state universe, where these big bangs are popping off repeatedly, perhaps an infinite number, all popping up within some expanding substratum. And there are genuine prospects that physicists may, in the coming decades, pin down the relevant physics. Now, this will be done by indirect tests. We're not going to be able to directly observe these huge energies, but there is a hope that there may be a theory which will explain many things we can observe. And of course, if you have a theory that gains credibility by explaining things we can observe, then you take seriously what its consequences are, even when we can't directly observe them. It's not true that you have to be able to test every consequence of a theory to take it seriously. For instance, in the case of Einstein's theory of relativity, we take seriously what it says about the insides of black holes where we can't observe, because it's been vindicated by many tests of regions where we can observe. So likewise, we may have a theory that allows us to put on a firm footing these ideas. Now, if there are many Big Bangs, or if the universe is much vaster than the volume we can see, a further question then arises. Are the laws of physics unique? This is a less poetic version of the famous question that Einstein once posed: did God have any choice when he created the universe? Well, we have strong evidence that the same laws apply everywhere we look. A distant galaxy, when you take its spectrum, gives you light from identical atoms to those we observe. But does this uniformity extend to other Big Bangs? In fact, the most popular theory, called string theory, suggests the answer is no. Theorists suspect, for reasons quite independent of cosmology, that the substratum of space, what's called the vacuum, might display immense variety. Were that the case, then different Big Bangs would cool down differently, ending up governed by different laws. Some laws would be more propitious for the evolution of complexity than others, and we naturally would find ourselves in one where things were propitious. But then we would have a situation when at least some of what we thought of as laws of nature were, in this grander perspective, parochial bylaws just in our cosmic patch, a patch which is a tiny part of this huge microverse. And there's a large literature on this, which I won't go into. But just to emphasize that support or refutation for these conjectures must await firmer links between the theories of the very large, the cosmos, and the very small, the quantum. But they are speculative science, not metaphysics. And physicists may eventually discover which aspects of nature are direct consequences of bedrock theory, a theory which would apply to the entire multiverse, and which are sort of environmental accidents. There's a nice analogy given by Paul Davies: snowflakes. Snowflakes all have hexagonal symmetry. That's because that's a feature of the water molecule. But they have different patterns because the way a snowflake grows depends on the detailed humidity and temperature changes in the cloud where it forms. So the question is, which of the physical laws are like the hexagonal symmetry, part of the bedrock multiverse fundamental laws, and which are environmental accident to the way our particular Big Bang cooled down? So we've learnt that we live in a solar system which is just one planetary system among billions, in one galaxy among billions, but there are intimations that a further Copernican demotion may lie ahead, because the entire panorama that astronomers may observe could be just a tiny part of the aftermath of our Big Bang, which is itself just one of an infinite ensemble. Our cosmic environment could be richly textured on this grand scale, and so we may be unaware of the big picture, just as a plankton in a spoonful of water is unaware of the complexities of our world. Well, how seriously should we take all this? As I say, it is based on the most convincing theories we have now, but that's still speculative. In fact, there was a conference at Stanford University when we were asked by the audience, how seriously do we take the multiverse concept in general? And I said, on the scale, would you bet your goldfish, your dog, or your life? I was about at the dog level. And then Andrei Linde, who'd worked for 25 years on the inflation universe, said, well, you'd almost bet a life on it. And then Freeman, Stephen Weinberg, the great theorist, he said, well, he'd happily bet Martin Rees's dog and Andre Linde's life. Well, how far in the future does a full understanding of all this lie? Einstein averred that the most incomprehensible thing about the universe is that it is comprehensible. He was right to be astonished, because our minds haven't changed much since our ancestors roamed the African savannah. And it's amazing they can contemplate so much of the microworld of atoms and the vastness of the cosmos. But some aspects of reality, a unified theory of physics or of consciousness, might elude us simply because they're beyond human brains, just as surely as a monkey is unaware of quantum theory. There's no particular reason, it seems to me, why the human brain should be matched to understanding all aspects of reality. And before finishing, let me explain why I think that's a relevant argument by focusing back closer to the here and now. I'm often asked, is there a special perspective which astronomers can offer to philosophy and our general view of our place in nature? I think the main thing we can offer is a mindfulness of the immense future lying ahead. The huge time spans of the evolutionary past are now part of common culture. Our present biosphere is the outcome of more than 4 billion years of evolution. But most people, while aware of this, somehow think that we humans are the culmination of the evolutionary tree. I don't think any astronomer could believe that. Our sun formed 4.5 billion years ago, but it's got 6 billion years more before the fuel runs out. And the expanding universe will continue, perhaps forever, destined to become ever colder, ever emptier. To quote Woody Allen, eternity is very long, especially towards the end. So any creatures witnessing the sun's demise 6 billion years hence, they won't be human. They'll be as different from us as we are from a bug. Post-human evolution, here on Earth and beyond, could be as prolonged as the Darwinian evolution has led to us, and even more wonderful. Indeed, I'd strengthen that statement by saying that future evolution will happen much faster than Darwinian selection, because it'll happen perhaps on a technological timescale. If a few hundred years from now, independent groups are living away from the Earth in space, then good luck to them, surely, whatever constraints we impose on these techniques here on Earth in adapting their progeny by genetic modification to fit in their new environment. And then the human species will diverge, the post-human era will begin. And that could be in centuries rather than in millions of years of evolution by natural selection. But my final thought is that even in this concertina timeline that astronomers envisage, extending 45 million centuries into the past and 60 million centuries into the future, this century may be a defining moment, because it's the first in our planet's history when one species, namely ours, has the Earth's future in its hands and could jeopardize this immense potential I've outlined. So this pale blue dot in the cosmos is a special place, maybe a unique place, and we're its stewards at a especially crucial time. And that, I think, is a message for all of us, whether we are astronomers or not. Thank you very much.
Well, thank you very much, Martin, for that great talk. Next talk is by Freeman Dyson, one of the great pioneers of quantum field theory and a long-time inhabitant of the Institute of Advanced Studies near Princeton. Freeman.
So, well, thanks to everybody who had a hand in inviting us here. It's great to meet so many old friends and new friends as well. First of all, I take a much more limited view of science than Martin. I think, science is a bunch of tools which have been helpful for solving some technical problems, but they don't by themselves give any great insight. And if you look at religion, it really has nothing to do with science. It has much closer links with religion, with literature, or with art, or with architecture, or music. All of those things are much closer to religion than science is. And so it's sort of, if you want to talk about science and religion, I would say you're probably barking up the wrong tree. And if you look at history and who have been the great influences on the growth of understanding of religion, you might say, well, Dante and Milton, perhaps the two that had the greatest influence. Dante wrote the Divina Commedia, Milton wrote Paradise Lost. These are works of science fiction, if you like. They are theological fiction, which throw a deep light on the deep problems of existence. In comparison, take Newton, who was the biggest scientist who ever lived, and tried very hard to do something in theology, but failed miserably. And the actual contributions of Newton in the theological area are a great disappointment. I mean, both to him and to theologians. So even Newton couldn't do it, so what hope is there for us? The fact is that, in my opinion, we have much more to learn from the poets than from the scientists when it comes to problems of human destiny or the purpose of the universe or all these big questions. Sir John Templeton was well aware of this, and in fact, in the year 2000, the same year I got the Templeton Prize, I was also invited here to London to a conference organized by Sir John on the subject of Olaf Stapledon. Olaf Stapledon is really the inventor of the multiverse. He is the first writer, as far as I know, who gave a convincing picture of the multiverse. And of course, it's pure fiction. It was a novel which he wrote called Star Maker. And anyway, Sir John read that and was very much impressed by it, as I was too. And I think that, so he organized this meeting in London, which some of you may have attended, in which science fiction writers mingled with theologians, and it was a great, very fine meeting. Unfortunately, it has not been very much followed up. But in any case, the people who were, in my view, the sort of the major contributors to theological thinking in the last 100 years have all been people who are sort of marketed as science fiction writers, actually are theological fiction writers, starting with Olaf Stapledon, then going on with C.S. Lewis, who wrote the Screwtape Letters, a wonderful book about Satan and how he operates. And Screwtape was a senior devil working for Satan, and these were letters that he wrote to his nephew explaining how to lead people astray. And it's a beautiful job, explaining how evil actually works. And then there was Ursula Le Guin, A Wrinkle in Time. There was Octavia Butler, who is my favorite, in fact, a black lady from California, who wrote 2 books called The Parable of the Sower and The Parable of the Talents, which are a wonderful story of the sort of collapse of civilization in California as it might happen in the next 50 years. She understood the American scene extremely well, and having grown up poor and black, she understood how tough life could be. So this is a society in which California is a desert. The climate has changed, so there's no longer any rain in California. And the rich are living in fortresses, and the rest of humanity, which is mostly people like her, outside the gates, just struggling to survive. And so she leads a bunch of pioneers with a new religion called Earthseed, looking to the future. And it's full of thoughts and full of poetry, very fine writing. And in the end, she takes off to the stars, which is, of course, the objective of this new religion. She doesn't quite, she's like Moses, she doesn't quite make it to the promised land, her ashes are carried on the first starship to the stars. Anyhow, and some of her disciples, in fact, are still pursuing this religion. It is still alive and well in California. Another lady who was here in London at that time, Mary Russell, I only got to know through that meeting, and also a writer of fiction, who is a very interesting character. She is a woman who began her life as a Catholic and ended up as a Jewish convert. So she understands the Catholic culture and also the Jewish culture. And so she has a story of a planet where there are two species sort of occupying the roles of masters and slaves, except they're different species, but both intelligent. And the master race, of course, is befriended by a Catholic priest, and the slave race, the slave species, is befriended by this Jewish girl. And so they both of them become leaders of the opposite sides in this a war of extermination, which ends finally with the victory of the slaves, of course, and the few surviving masters are put properly in their places. Anyhow, I find this all throws much more light on human destiny than arguments about the shape and size of the universe or any of the other wonderful things the astronomers are doing. I love astronomy. Astronomy is my trade in a way. It's a great pursuit. It's exploring a wonderful universe, and we're discovering more and more. But the idea that that's really telling us anything about the purpose of the whole thing, I think is very unlikely to work out. Much more will probably be learned in the next 20 years from the neurologists. I look to neurology as the coming science, probably for the next 100 years. I mean, we are making very rapid progress in finding out how brains actually work. We don't have the tools. We have only very crude instruments like magnetic resonance imaging, which has a very poor resolution in space and time. All it measures actually is flow of blood. And flow of blood doesn't really tell you what the neurons are doing, but it tells you a lot. And so we are learning a lot from the instruments that we have, but we shall have much better instruments. I see a future for neurology which will be not too different from what has happened to astronomy, that it will become data rich. It will reach the point where it's cheaper to collect data than to understand it. That's, of course, a situation that's already been reached in many areas of life, also in history and all aspects of life. We are drowning in information which we don't yet understand. So that will happen in neurology too, but we haven't even reached that point yet. So what's going to happen? We'll have, if you look at the actual bandwidth of a human brain, it's actually quite comparable with what we can handle with existing electronics, because you have an advantage roughly of a factor of 1,000,000, that a neuron has a bandwidth of about 1 kilohertz, whereas a microwave detector has a bandwidth of about 1 gigahertz, about 1,000,000 times greater. So it means you need about 1 detector for every 1,000,000 neurons. And so you have about 100, maybe 100 American billion neurons in your head. And so that means 100,000 detectors would be needed. So you could imagine that you'd have a monitoring system that could actually process the activity of a brain, observing each neuron and on a separate bandwidth, detecting the output of a brain in absolute detail with about 100,000 receivers. And that's not an astronomical number. It's a number that we can easily imagine, having some sort of a helmet on your head that would do that. So I look forward to neurology as the main source of information about the state of our minds, which to me is far more relevant to religion than the state of the cosmos. And anyhow, we shall see. But I like to put this in connection with another very, very lively issue which I happen to be involved with, which is the question of analog computing versus digital computing. That we all grew up, those of us who are old, with analog computers in the shape of slide rules. Slide rules, of course, were wonderful for practical purposes. They were analog devices which everybody used in the old times for doing simple calculations. Now, of course, they're considered to be totally obsolete. Instead, we have a little computer that gives you 7-figure accuracy and much quicker and much more versatile. So the general belief is that the digital age is the future and the analog age is the past. However, I don't think that's true. If you look, in fact, at the mathematics, there was a fellow called Turing, Alan Turing, who was the sort of grandfather of the digital age, and he came from the side of logic, that he was a student of mathematical logic, and he invented the notion of computability. He wrote a wonderful paper in 1936 called On Computable Numbers, in which he demonstrated two things. First of all, the existence of a universal computer that could do everything that any digital computer could do, so that you could actually build a universal machine that could be programmed to imitate any digital computer. So it would be able to answer any question that you could solve by digital means. And he also said, the second theorem he proved is that there are questions which that universal computer could not answer, particularly a thing called the halting problem, that whether a given machine, given a problem, would come to a halt or not. That's an undecidable question in a strict mathematical sense. Anyway, so that's what Turing did in the year 1936, which led to the computer age that we're living in. We put all our information into digital form. We have, it is now a digital world, and everybody believes that's going to last. I have suspicions it's not going to last. And there's another mathematical paper, which people are not so much aware of, by two gentlemen called Pourel and Richards in 1981 in the journal called Advances in Mathematics, which is proving that, in fact, there are numbers which are computable analog, which are not computable digital. That's also a mathematical theorem. So there are well-defined questions that could be decided by an analog computer which cannot be decided by a digital computer. So in a certain sense, in a mathematical sense, analog computing is more powerful. And I believe that that is, in fact, the reason why artificial intelligence has been such a total flop. We have been promised for 50 years that we would have artificial intelligence, that is, computers that could really think like humans and be intelligent in some practical fashion. And of course, that's been a dismal failure. And I think the probable reason is that all our machines are digital, but the human brain is probably analog. And the reason I think the human brain is analog, of course, I'm not an expert, but it's if you look at what we're really doing all the time, what we're really good at is comparing pictures in memory, that you look at a face and you know immediately, that's Martin, that's my friend Martin Rees. And how do you know that? Well, because you pull the memory out of your store, make the comparison in a fraction of a second. And in the same fashion, he says something, you immediately understand what he says because you're comparing a sequence of words with something in your memory. So that this ability to rapidly compare either visual scenes or auditory sequences is something we're born with, which is much more powerful than arithmetic, which is something we have to learn. So in our brains, the comparison of images came before the ability to calculate numbers. Anyhow, that's my conjecture. So I would expect that when there finally is a artificial intelligence, it will actually be analog and not digital. And so that's something that will have a profound effect. When we know how to build machines that do resemble our brains, of course, we will be in a different world again. So that's my pitch for the future. If you really want to understand the nature of the universe in some deep sense, if you want to understand its purpose, what we really want to understand is mind. We want to understand good and evil. We want to understand emotion. We want to understand human factors much more than galaxies and planets. So thank you very much. That's enough.
Well, thank you, Freeman, for that really wonderful and thought-provoking lecture. Our final speaker in this session is John Barrow, who is a most prolific writer of popular books on science, and one of his most influential serious books was his book on the anthropic principle in cosmology, which was focused a huge debate about why the universe is of such a nature as to allow us to exist.
Well, thank you again for the organisers for their invitation. We are asked on our invitation and on the programme to reflect on how the ideas we set forth in our Gifford lectures may or may not have changed over time. Unfortunately, my lectures were so long ago, 24 years I just calculated, 1988, that an awful lot has changed in some respects, although I don't believe the basic argument that I was trying to make has been affected by what has happened, and you'll see why in a moment. So the aim of my lectures long ago was to explore the nature of suddenly fashionable theories of everything and to explore what they could and could not tell you about the nature of the universe, particularly about the physical universe. To most outsiders, the ordinary person that you stop in the street, a theory of everything was imagined to do exactly what it said on the can, explain everything. Alas, the true reality of things is very far from that. Complete explanation is something that you only find in mythological accounts of the world, where there was a deep terror, really, of anything remaining unexplained or arbitrary about the nature of the world. So pre-scientific accounts of the world were generally theories of everything. Everything had its place, and there was a place for everything. Modern theories of everything are not like that. In ancient accounts, even chance was something that wasn't really left to chance. It was the action of the gods themselves, and therefore not something that you would be well advised to try to study or turn into a type of mathematical theory. And indeed, the study of chance as a branch of mathematics develops incredibly late in the history of mathematics, even though people are playing games of chance back to the beginnings of time. So the point that was made in those lectures originally were the theories of everything of the physicist variety, although they're necessary for a complete scientific understanding of the world, are far from sufficient. That there are many other aspects of the world that we need to understand to add to our description of reality if we're going to claim to have a full picture. And the other ingredients I talked about, in brief, were things like initial conditions for the universe, the nature of the forces and particles at work in the universe, the laws of nature, of course, the constants of nature. But more interestingly then, the breaking of symmetries, the haphazard outcome of events in the universe, the presence of organizing principles and selection effects, which filtered the type of evidence that it was possible for us to gather, and therefore the conclusions we would draw from it. And finally, some influences of what Kantians would call categories of thought. Well, in a moment, I'll highlight some of the things that have happened in each of those areas since 1988. But let's just make a few general comments. The whole idea of a theory of everything, which you can find in 20th century physics, almost back to its beginnings, was really a reflection of a type of what one might call religious, in inverted commas, belief of particularly physicists. They like unification. They like their universe to be governed by one God rather than four. And so the fact that they have four perfectly good working laws of physics governing electromagnetism, governing gravity, governing radioactivity, governing nuclear forces is not sufficient. They don't like this divided legislation. They're looking for a scenario in which they can be joined together in a single overarching pattern. All of these theories are a variety that are known as gauge theories. They're very powerful. They require a certain symmetry to be preserved in the workings of nature. Sometimes that symmetry is rather abstract. But the preservation of that symmetry not only tells you how forces and particles behave, but also what forces and particles can exist. So it's as though the traffic laws told you something about the design and detailed structure of cars. And also the particles that these laws govern have the remarkable and inexplicable property, really, to physicists, they're all supposed to be identical. So the ultimate fine-tuning of nature, the fact that once you've seen one electron, you've seen them all. So the growth of physics in a sort of naive historical perspective is to go from more supposed forces of nature to less. So at first you think there's dynamic electricity and static electricity, and then you learn there's just electricity, and then Maxwell teaches you that there is not electricity and magnetism, but just electromagnetism, and then Weinberg and Salam teach you that there is not electromagnetism and the weak radioactive force, but a single electroweak force. So all the time you're going from more to less, and physicists have mapped out what would be the next steps in this reducing game with regard to the laws of nature. There is no observational confirmation of those last two steps, the addition of the strong nuclear force to the electroweak interaction to produce a so-called grand unified theory, and a final step, much trumpeted by the string theorists, of producing a so-called theory of everything by adding gravitation as well. But what's impressive about this scheme of things, if it comes to fruition, is that at the level of the laws of nature, the universe appears to be deeply simple. There are only perhaps 4 low-energy forces, and maybe at high energy just the one unified force. And so if you're in the habit of looking at the universe at the level of the laws of nature, you will be greatly impressed by its simplicity. But more interesting still, you will be most impressed not by the things you see around us, but by the laws of nature themselves. Very Platonic situation that what's most impressive to theoretical physicists in particular are the laws of nature, things that you don't see. But for other people, who may be biologists or neuroscientists, as Freeman alluded to, these people have not much interest in the laws of nature. No evolutionary biologist would ever use the term, because what those scientists deal with are the outcomes of the laws of nature. The outcomes of the laws of nature are far more complicated, far less symmetrical, much harder to understand than the laws themselves. And that's why science is so difficult. We see around us these asymmetrical outcomes, and we have to somehow work backwards and reconstruct the simple symmetrical laws behind them. So for the biologist, what you're looking for are these little bylaws that Martin alluded to in another situation, things that govern the outcomes of stability and natural selection that win out in the long run. And those things don't have to be symmetrical or beautiful or simple in any way. They just have to be stable. And so for the whole discussion of whether the world is simple or whether it's complicated, you can see that the messy scientist, the biology specialist, or the squalid state physicist who deal with all these complicated outcomes, the world does indeed look rather complicated because they are close to the world of the asymmetrical outcomes. And if you then start to engage in a dialogue between science and religion, you can see how confusing and confused the dialogue can become once you start mixing together fundamental physicists and their subjects and biologists or psychologists. Because for the fundamental physicist, it's that pristine world of the perfect symmetries that's the real imprint, the mark of the universe. And they're very used to the true reality, as it were, the ultimate reality being the things that you don't see, those laws. For the evolutionary biologist, the Richard Dawkins, as it were, of the world, things are completely different. Biologists are used to dealing with the nitty-gritty of hard facts and observable outcomes. They don't talk about laws of nature and symmetries and this hidden reality behind the appearances. And so the whole issue of encountering science and religion would perhaps do well to recognize this type of divide. The divide at the level of natural theology was really created by Newton himself. Aside from Newton, the whole great tangled subject of design arguments and arguments from design in natural theology was always about the fortuitous nature of the outcomes of the laws of nature. That my hand just happens to be the right distance from my shoulder so that I can put my food in my mouth, as it were, or that habitats for animals seem to be tailor-made for their requirements. This is a design argument based upon the outcomes of the laws of nature. But Newton, with help from Martin's predecessor, Mr. Bentley, a master of Trinity, developed a completely new type of design argument that was based upon the laws of nature and their character rather than the outcomes. Well, this study of the complex outcomes was something that wasn't terribly fashionable or easy for a long time during the 20th century. And the big development that we've seen since the late 1970s and the 1980s has been the study of this world of complicated outcomes. It's been made possible because of technological developments in Silicon Valley and elsewhere, that these problems are too complicated to solve with pencil and paper in 30 minutes under examination conditions. So they tend not to be taught in schools or university courses. And you can only study them by experimental mathematics, by numerical simulation. And before the mid-1970s, there certainly were computers, but they were controlled by ferocious groups of highly funded individuals and dedicated for very specific blockbusting purposes, like predicting the weather or the economy or exploding stars or bombs, things of that sort. But all of a sudden, individuals could have little devices like this one here, which were extraordinarily powerful, and they could carry out their own investigations of complex and complicated systems. And this is why the study of chaos and complexity grew up hand in hand with the personal computer revolution. And we see today the huge expansion, really, of that area of understanding, even though over the same period, the growth in understanding in what we might call fundamental physics, particle physics, has really been quite slow, deep, and it's difficult to progress. But the great progress has been made in this study of the complex. Well, what are the highlights that one might pick if one was going through these different areas I talked about? The first, of course, was the replacement of the old, almost naive string theory, 5 different possible string theories that people used to worry about, by 10 to the power 500 different possible theories, by what is called M theory. And the old string theories were just shadows of views from different directions, as it were, of this as yet unfound M theory. One thing you learn from all these theories that's sombering is that they claim that they can only exist, and they have their prime feature, which is that they're finite, if the world has many more dimensions than the 3 space and 1 time that we walk around in and hold our meetings in. And this is got around by supposing that only 3 of them have become astronomically large, and there's only 1 time dimension. But The sobering thought is that even if that is true, the true reality, the true constants of nature, the true structure of physics doesn't live in the three dimensions where we carry out our measurements. All our measurements of so-called constants of nature are of things that are just accidentally constant because the other dimensions are not changing. So we are really separated completely in this scenario from getting an experimental grip directly on the true constants of nature and the true nature of fundamental physics. In the area of initial conditions, we've heard already the great success, observationally, of some aspects of the inflationary universe theory and its extrapolation into the idea of eternal inflation, and the idea that we inhabit one greatly expanded region like a bubble in a vast foam, infinite foam of bubbles. Curiously, the old question of did the universe have a beginning has two answers really now. Our little bubble, as it were, could indeed have had a beginning, and probably did in this theory, but it's not a Big Bang beginning. It's a rather soft, quantumish beginning. But the whole multiverse, the whole panoply of all the bubbles, as it were, might have a beginning. It doesn't have to have a beginning, but it might well have done. So the question of did the universe have a beginning is rather nuanced in this theory. But cosmologists ask the question, did the universe have a beginning, far less often now than they did in 1988. And that's, I think, a consequence of the success of the inflationary universe perspective, which gives us a prediction as to what the universe should be like today, largely irrespective of how it began, or even if it began. There are many positive features of this that you can hope to explain the universe you see today independently of how it began. And since you believe you'll never know the details of how it began and what it was like, that might be a rather good thing. The other side of the coin is that you cannot expect, by making observations in the universe today, to learn anything about what its structure was, if and when it began. Well, in the area of forces and particles, we know that CERN is busily trying to convince us and claims that it will be able to, by the end of this year, that the Higgs boson exists, and maybe later that supersymmetry exists. In the area of the constants of nature, the great discovery there is of the cosmological constant, that everybody was expecting did not exist and was discovered, in effect, or something that's for all practical purposes like it, by astronomers who received the Nobel Prize just over a year ago for that discovery. So we've discovered that the universe is dominated by an anti-gravitating form of energy. It's known as dark energy. It's causing the universe to accelerate at present. And explaining this quantity, why it has the strange numerical value that it does, confirming that it really is the so-called cosmological constant, is the great challenge of modern astronomy and fundamental physics. And the curious aspect of this is that there might not be an explanation for this quantity. String theorists really don't like this idea. They, of course, actually have no explanation either. But it could just be one of these random outcomes. So if you have lots of metal bars, iron bars, and you cool them down, they will randomly magnetize. You won't be able to predict which will be the North Pole and which will be the South Pole on one piece of iron, but roughly half and half will be in each orientation. And the example I like to give, long ago there at those lectures, was it's a bit like going back to 1600 and talking to Kepler. And if you asked Kepler, how can you explain the number of planets in the solar system? So Kepler would have believed that there was a deep, fundamental, Pythagorean-like symmetrical principle as to why there was the number of planets in the solar system that we observed. Today, no astronaut, no astronomer working in planetary astrophysics in their right mind would try to explain the number of planets in the solar system. It's just a random accident. It's like the number of people who happen to be waiting at the bus stop down the road. It just falls out by a concatenation of accidents. So it could be that in the future that there are many things that we fondly imagine are going to be fundamental and fundamentally explained, that are going to turn out to be random outcomes of some symmetry-breaking process. And all we can say about them is that there's an ensemble of possibilities from which they fall out, and they better fall out in such a way as to allow observers and astronomers to exist later on in the universe and talk about the problem. Well, the last two little things then to mention, this that I alluded to earlier, the study of complexity meant that we had to understand what we might call organizing principles. We know one type of thing like this, which is very far-reaching and universal, and that's thermodynamics. But it had always been the hope of people studying complexity and chaotic systems that there might be other bylaws, or maybe even just one bylaw, that governed the way extremely complex organized structures developed. And there were nice paradigms. If you pour sand down to make a pile of sand, then even though the trajectory of each individual grain of sand is chaotically unpredictable, can't predict what side of the pile it will fall, you end up with a pile that will eventually attain a particular slope, angle of repose. And if you add more sand, you'll just precipitate more avalanches which sustain the same slope. So here there is a large-scale ordering process that develops or emerges out of individually unpredictable events. So far there's not been found any general principle of that sort, and it's probably too much to hope for that such an all-encompassing principle exists. But there may well exist groups or equivalence classes of complex processes that share the same features. The second last topic I talked about, alluded to already, there's not reason to say much about it, was selection effects. So the way in which, if you have a theory of the universe that has unavoidable random aspects in its early evolution and initial state, then you cannot compare theory and observation reliably unless you take into account the conditions needed for the existence of observers. So in modern cosmology, the fashionable calculation to try and perform, so far not done, is to calculate the probability distributions of the observable outcomes from the inflationary and eternal inflationary universe. So if those probability distributions were found, what do you compare them with? So do you take the most probable outcome that the distribution predicts? Maybe not, because if the most probable outcome doesn't allow there to be any atoms or planets or astronomers, it's not the relevant one to confront theory and observation with. So unless you understand this point, you will draw the wrong conclusions when you come to test theory and observation, just as in the laboratory, if you are unaware of selection effects in an experimental setup, you will draw the wrong conclusions from the experimental evidence. Well, finally, categories of thought was the last thing I talked about, and our ways of thinking about the universe. There are some rather simple features that have come along. The issue of whether you should think of the universe as being continuous or discrete is one that's been challenged by Stephen Wolfram in the last decade. And he really did want to try to say something about the problem that Martin raised, about whether one should worry about the fact that our computational complexity as our brains was similar to that of the universe we see around us. He would argue really that both were maximal. And lastly, we often hear the statement about the unreasonable effectiveness of mathematics in the physical sciences. That may or may not be, but set against it, I think, is the unreasonable ineffectiveness of mathematics in areas like economics, understanding human behavior, sociology, in fact, most of human experience that involves complex, self-interacting agents. So I think that's a good place to stop. Hand over to George again. Thank you.
Thank you. Okay, well, we've had some really interesting talks. There's now time until past for questions. You can ask any or all of the members of the panel something to do with what was said.
Yeah, astronomy and other things play a role in religion. Now, I'm Mr. R. Nijjar, retired lecturer of metallurgy, preaching Christianity and Sikhism. Now, this concept of astronomy, if we take sun to God, and Christ Jesus came in his line, and moon to John the Baptist, witness to the light but not the light, then we can study theology very easily. Remember that when Jesus was tried, Pilate went outside in the sun to wash his hand, meaning that he had nothing to do with Jesus. But the temple priest people, they were shouting, "Crucify him." So that's why he handed them over to Jews. Do what you like to do. So Pilate had nothing to do with the killing of Jesus. So if you apply such thing, to theology, what is in universe duplicated in your body. So if you can compare, then it will give you a good idea. Thank you.
Any response?
No comment.
Julian?
Julian Barber, a question for Freeman Dyson. Newton was not a very good theologian. What's your estimate of Leibniz?
Oh, I'm not an expert. I don't pass judgment at all. I mean, I've not read a word of Leibniz. I have read a good deal about Newton, but whether Leibniz did any better, I couldn't tell you.
I'm just going to make one remark from the chair, which is that people skirted on this idea of infinity once or twice. I believe very strongly that, in fact, following some other thinkers, that infinity never occurs in physical reality, that infinity is a mathematical concept which is important for mathematics, but as David Hilbert said, it never occurs in physical reality. And I think people have forgotten the true nature of infinity. Infinity is not a very big number, and people talk as if it's a very big number. Infinity is an unattainable number. It doesn't matter how far you've got, how much you've counted, you are still not even the first step to infinity. And I think that's a really important principle in some of these discussions about the nature of existence, particularly about the multiverse, where the word infinity is thrown around with gay abandon.
I can comment on that. Yes, I think Aristotle said that some years before Hilbert. I think, the multiverse is about potential infinities, not about actual infinities. So we're quite happy to talk about the universe being infinite, or there being an infinite number of particles in it. But probably following Aristotle, we're rather nervous about there being actual infinities that can hit us here and now. I think there are two interesting things to say about that, is that when people talk about the infinite, somehow they're always biased to think about the infinitely large. But the infinitely small is much more interesting because it's right here on your hand. And Pascal worried about that just as much as the infinitely large. In physics, if we come across a prediction that something is infinite, and if we're just humble fluid mechanicists, plumbers if you like, we might predict that something happens infinitely rapidly when a shock wave forms. But the signal is just that we haven't modeled the situation in full detail, and if we add the friction of the air, then the change becomes very, very rapid rather than infinitely rapid. So I think just because an infinity shows up doesn't mean the theory is wrong or hopeless. It just means it's incomplete in some respect, that you've got to try harder. And people hope that these infinite singularities or changes will then be smoothed away. But so it's like a first-order approximation to something that you hope that you'll then model better. People like Roger Penrose would disagree completely. So Roger thinks that infinities in the centre of black holes or at the beginning of the universe are absolutely essential boundary conditions in the universe. But because they're at the beginning of the universe or the end of the universe, they really are special. And there's no more special place than the beginning of the universe. So he's happy for that to occur there. But he's probably unusual in that respect. Particle physicists used to spending 50 years, led by people like Freeman, trying to get rid of infinities. And at the same time, cosmologists were very happy to introduce them and accommodate them at initial singularities and final singularities.
Martin?
I'd just like to say, I don't think there's anything in these theories where actual infinity is different from some very large number like a googolplex. I don't think you're right in saying that infinity is important for these theories.
They're all potential infinities. They're potential infinities.
Thank you. I have a question that was stimulated by something Martin Rees said, but it's about language, and I think it could apply to all speakers. Martin gave the example of asking whether one could have a common language with an alien civilization, and I think it's very natural to suppose that mathematics and some of the basic physical sciences would offer a language. But I think that it's a little feeble to stop there. I think that much is pretty clear. The interesting question is, well, what about our other languages? And I particularly mean things about aesthetics and also what constitutes moral character, things of that kind, which admittedly are more subtle, but you could argue are, there's a reasonable uniformity across human culture, at least to some extent, and I'd like to maybe invite you to reflect on that. Whether an alien would think that he, alien, or it, she, whatever, ought not to do to, cousin alien things that would not wish cousin alien to do to it herself. Would they think in that way? Do you think it's likely? Can we have any common sense about that?
Okay.
Well, let's think about something that people probably think would be shared. I mean, mathematics and the mathematics used in physics. Imagine the following little story, that you've made contact with some extraterrestrial beings, and it's clear that they know, all the clay $1 million problems. They know the answers to all these problems, and you're waiting for them to download to you how they found these answers. And mathematicians are looking forward to learning all sorts of wonderful new arguments and logical procedures that they will then be able to apply elsewhere. But they're deeply disappointed because it turns out this advanced civilization does all mathematics experimentally. It's long given up the idea of proving theorems and so forth, incredibly laborious and slow. So they do all mathematics using very fast computers, and all results have confidence intervals then attached to them. So they can then sidestep restrictions from Gödel and others and get much, much further. So when they've solved Fermat's last theorem, it just means that they've done an absolutely massive computer search and they put a statistical significance on it. So there might be something even in such a well-defined area as mathematics that's sort of surprising and completely different about the way other people do things. And they can do any form of technology that you wish with that way of proceeding. They've got lots of silicon on their planet, so they invented computers very early in their evolution.
Yes, I mean, I think if things could be different in mathematics, then I'd have thought they could be so inconceivably different from us that we could not relate to them in any other way. So I think even whatever life exists 10,000 years from now might be so different from us that we could not relate to it. So I would be sceptical of any real contact other than on the physical world. I'd just like to say one thing about the limit of understanding. I said in my talk that I thought there might be some things beyond human brains. I'd said it before, and in his, I thought, excellent book, The Beginning of Infinity, David Deutsch attacked me. He said that all these problems could, in principle, be computerized and you could solve them all. And my response to that is, well, maybe, but it's not the same as understanding. Let me give an example. You probably know about the Mandelbrot set, a very complicated pattern. If I asked you to visualize the surface x squared plus y squared less than 1 in a Cartesian plane, you can probably say, well, you can visualize a circle, unit radius. If I give you the recipe for the Mandelbrot set, then you need a superhuman intellect to be actually able to visualize what that means, although we can compute it. So when I said the limits to human comprehension, I meant in the sense of visualization and really getting a grasp of the basic idea rather than the ability to compute. So there may be no limit to computation in principle, but I think there is a limit to what we can actually understand.
Yeah, I'd like to present a piece of experimental data. There is a lady whom I know well called Jessica Park, who is autistic, and she has a totally different universe from ours. I mean, she is really the closest I've ever come to an alien intelligence, and so alien that, I mean, when she was a child, she would use the word I and you interchangeably. There was no concept for her of personal identity. She didn't distinguish between herself and other people. So her world was certainly radically different from ours in all sorts of ways, and there were many things in our culture that she had no way to understand. But one thing we had in common was the prime numbers. Her primes were the same as ours.
Well, if you encounter one of these super intellects and you ask them, ought one to keep promises, what answer would you expect?
No different a variety of answers than you would get, yes, no, and maybe.
Yeah.
The three answers you'll get on Earth, and you would expect to get the same answers.
Thank you. I've long been interested in a limitation in Newton's work, because he couldn't solve the three-body problem. And we now know, of course, the three-body problem can't be solved analytically. But as a former physicist, I've been struck by the fact that so much of our modern physics is ultimately about two-body systems, or aggregates of two-body systems, or perturbations of two-body systems. Moving to the complex case, do you think that's a difference of kind or just of degree? And if it's a difference of kind, what should physics look like in the future? Thank you.
Martin? I think clearly there are going to be limits to what we can predict. Chaotic systems, etc. And people talk about the limits set by quantum uncertainty. That's not the only one. I mean, Michael Berry's given a nice example of a billiard table with frictionless billiard balls. Quantum uncertainty comes in after, say, 25 collisions, but after about 40 collisions, the gravitational force of one electron at the edge of the universe introduces enough uncertainty. So the limits to predictability are very serious and are completely insurmountable. And that's something we have to contend with, obviously in weather forecasting and other areas, but in lots of cases.
No, I would like to add that the whole point of science is that it's unpredictable, that in fact, if it wasn't a surprise, it wouldn't be science. And science is about the things we don't know, but not about the things we do know. And so what's going to happen in the next 100 years is just one surprise after another. And it's pointless to say what you think is going to happen. The definition of a really important discovery is that nobody expected it. And in fact, nature's imagination is just much richer than ours. And that's something for which I'm profoundly thankful.
I think in these sorts of problems, like the one that Martin mentions about chaotic systems, you think then about asking a different question. So in this room, for example, every single molecule is moving chaotically. It's bouncing off other molecules in some sense like the balls on the billiard table, but with much more uncertainty being added in each collision than the billiards. And so you might think it's completely hopeless to try and understand what's going on to the molecules in this room. But at school we learn Boyle's law. pressure times the volume over the temperature is a constant. And the temperature is just a measure of the average speed of the molecules, and the pressure of is the average force per unit area on the walls. And so by thinking about the average quantities, there's a very, very simple law that governs what happens to the molecules in this room. And so with complex systems, the challenge is to try to find these soluble, slowly changing relationships between the quantities. And God, the two-body problem. In general relativity, we can't solve the two-body problem. People say, you know, in quantum field theory, you can't even solve the one-body problem and all the zero-body problem. So.
Okay, well, we're slightly going to overtime, but a quick question.
Thank you. Sarah Coakley, Cambridge. Martin, in your talk, you made an aside in which you clarified that you were doing speculative science and not metaphysics. Mm-hmm. But it struck me that all three of you made some remarks that sounded astonishing like metaphysical claims. Would you like to clarify further what you meant by that distinction?
Well, I think I understand what I mean by speculative science. I don't think I understand what is meant by metaphysics, and that's why I don't use the word. But I think just to put a footnote to what John Barrow said, a sort of anti-reductionist statement, even if we could solve the Schrödinger's equation exactly for a complex system, it wouldn't tell us anything interesting. I mean, every science has its own non-reduced concepts. Even in the physical world, say if you're a fluid mechanic expert trying to understand breaking waves and things, you treat the water as a fluid, you don't care about the atoms. So I think we have physics as a science, we have other sciences which are in a sort of hierarchy, each with their independent concepts. I would say things that aren't physics can be described as other sciences.
Any other closing remarks from any of you? No. Okay, that is the end of that session. I want you to thank our speakers again for a really interesting set of talks.